So we continue. We are going to have a look of the OpenMP parallel program. How the programmer is going to program the system using this OpenMP parallel programming paradigm, and how this OpenMP code is going to work on the system. Now, OpenMP programming is limited to a node, to a server. So a node, a server means that basically you have only one operating system instance for your node or for your server. You have only one operating system, and the operating system is managing all these components of the server. The mainstream servers right now from the marketplace, you have two sockets. Suppose you have two sockets, you have 64 sockets you have 64 cores per socket, and you are going to have 128 cores for the server. It's quite a lot of cores. It's quite a lot of computing power. So OpenMP program runs on the server. It is going to make use of all these cores to run a piece of code to do the parallel computing. Let's have a look. Let's read through this piece of code to understand how it works. Okay, now for OpenMP program, when we talk about this kind of OpenMP program, we are going to use threads. Everything will be threads. For MPI communication, for MPI parallel programming or MPI parallel computing, we use the word MPI process. But for OpenMP programming, we are going to use the word thread. So we are going to see thread 0, thread 1, thread 2. Okay, suppose for our particular example, we are going to have 128 cores. So we are going to have one thread per core. That means we are going to have 128 cores. So the last one is going to be thread 127. Okay, fine. This is okay. Now, the fact is that for an OpenMP program, all these threads will be running on different cores from the same node, and all these threads can access the shared memory of a node. Okay. Now let's have a look at this piece of code. This is a piece of C code. The starting point is this main function. We are going to start running this piece of code. And the starting point is the main function. And after it starts running, the first thing it's going to do is going to declare two variables, partial sum and the total sum. Okay, two variables. Okay, and then right now, up to now, we are going to have only one thread running on the system because we launch this piece of code is going to start running on only one thread and is going to be running on only one core. You have 128 cores, but it's going to be running on only one core, and this thread is called thread 0. This is the first one, is called thread 0. Okay, and then we continue. Afterwards, what we are going to have is this parallel region. Okay, this is the starting and this is the end of the parallel region. So Pragma OMP means that you are going to go through, you are going to get into a parallel region. And for this particular parallel region, there are two declarations, is private and shared. Means what? Means, okay, you have declared two variables. The two variables when we get into this parallel region, the two variables will be different. One of them will be private variable, and the other one will be a shared variable. What does that mean? It means that as is written here, is going to be shared and to be private. But how that? What's that? Okay. Now, there is an environment parameter which is called num number of threads. Maybe this one thread. We just read this thread numbers. Thread numbers for our particular case, we can set to 128. It means what? It means you launch your OpenMP code. At the beginning, you have only thread 0 working, running on one core, run this piece of code. But when you come across a block of parallel region, I mean, you come across a parallel region, and then before getting into this parallel region, the system is going to give you much more threads as indicated by the environment parameter. If the environment parameter is 128, that means the system is going to create for you another 127 threads to join thread 0, and you are going to have 120 threads. And all of a sudden, when you come across this parallel region, you are going to have 120 threads. Okay, you have so many threads. There is a kind of trouble. So what we are going to do, the system here, it has been cleared. Okay, for your guys, these 128 threads, the variable total sum is going to be shared. So that means this variable could be read and write by all these threads. That's shared. So what should it is? Should this variable be located? It should be located in the shared memory, because this is shared. So it's the total sum is going to be located in the shared memory because it's total sum. Okay, it's shared memory. And then there is also this private sum. The system, when we get into this parallel region, it has been declared that this partial sum is not shared, is private. So each thread, all your guys, each guy is you are going to have your private sum. You are going to have the partial sum as your private data. So this thread 0 is going to have its partial sum. Partial sum as is private data. Okay, so I'm sorry, I should change the color. So the first one well, I'm going to remove the old one. Okay, I'm going to remove the old one. I'm going to do it again. Is that okay? The first guy is going to have this partial sum. Okay, this is your private data. Thread 0 is your private one. No other guys can access this one. And for thread 1, what we are going to have? Okay, thread 1, you are going to have your private data, which is partial sum. Again, it's called partial sum. Okay, this is your private data. No other guys can access it. And then again, we are going to have another one for the third one. Third one is partial partial sum as is private data. And for all the 128 guys, 128 thread, each thread is going to have its own partial sum. as is private data. So, I need to explain a little bit more here is that this drawing is good to understand all this, but it is a little bit misleading. We have to be careful here is that we have all threads running on the cores. Thread 0 will be running on core 0. Suppose it's core 0, thread 1 is going to be running on core 1, etc., etc. And let's make it clear is that here, what we have here is the memory hierarchy. What I mean is, why I mean memory hierarchy is that the total sum, because it's going to be shared between all these threads. So pretty much this total sum should be located in the main memory. Because we know that cache are, um, are associated with the cores, are associated with the sockets. So we have cache coherent protocol to help the system to run, but pretty much if you have a private thumb, there is a lot of chance that this partial sum, sometime point, this partial sum will be located in the cache, because this is private data. No other guys is going to access the private data of the other guys. So each one is going to have its own private data. There is a big chance that this data will be located in the cache. Okay, so here is the system. The drawing has been done this way. I need to make it clear that the private data and the shared memory, the private data is private, is data. We are talking about data. Its data is private. The private data, if you look at this drawing, it seems that this private data is not in the main memory. But again, this could be wrong. I mean, this partial data, this partial sum, which is private data of thread 0, it could be in the register, it could be in the cache, it could be in the main memory. Depends on the system, depending on the time point you are talking about this data. It could be somewhere in between the registered cache, the main memory. But again, we have to understand here the square in red. What I mean here is the memory hierarchy. It could be shared memory, it could be cache, it could be register. Okay, so we have this private partial sum is the private data for thread 0, etc., etc. And all of a sudden, you have these 120 threads here running together, starting from this parallel region. And what they are going to do, because right now, remember, you are not only thread 0, you have 128 threads. Okay? These 120 threads, they are going to running each line of code start from here. So each thread is going to set its own private partial sum as 0. And then each one is going to set the total sum, which is shared, to 0. Okay, that's good. That's fine. And then we are going to continue. We are going to come across this for loop. This for loop is to do the sum from 1 to 1000. Okay? 1 to 100, 1 to 100, 1 to 1000. Okay. But you have 128 threads. If 128 threads, each one is running the same for loop. It doesn't make any sense for all these threads to do the same thing. The target, the principle of parallel computing is to share the workload. So what am I going to do? The system is going to tell the 120 threads, okay, you have 128 guys. You need to share the workload. Right now, the workload is 1,000. So 1,000, which is workload, it needs to be shared by these 128 threads. Okay, so it's not so easy. What I'm going to suppose is 124 and divided by 128. And then, okay, so we are going to have 8. So what I'm going to do, the system is going to ask thread 0 to work on 1 to 8. You are going to sum 1 up to 8. The thread 1 is going to sum from 8 to from 9 to 16. Sorry, this is not 8, is 9. Okay, so it's 1 to 8 is 9 to 16. 9 to 16. And the third thread is going to do from 17 to 24, etc., etc. Okay? And we continue like this, and we know the last one, the 127, which one is going to be doing we know that the last one is going to have nothing to do. 120. There are 3 threads. They have nothing to do. It's going to be 127, 126, 125. Sorry, sorry for the writing. I changed. Better, I'm sorry. Better, I need to remove this one. So what I'm going to have is that this 125, they are going to have nothing to do, and 124. This guy is going to do from 993 to 1000. And then the 3 other guys, they are going to have nothing to do. Okay, so you have 128 threads. You have a workload, which is the summary of from 1 to 1000. And then you have this kind of arrangement. I mean, pretty much the system is going to arrange all these threads to work this way, because the first one you need to work from 1 to 8. The second one is you need to work from 9 to 16, and etc., etc. And there are 3 guys. They are going to have nothing to do. Okay, but right now because the limit is 1000. The other guy is going to have nothing to do. Okay, this is what's going to happen here. Here, what you can see here is that the workload has been shared by all these threads. Okay, and each thread is going to do its own piece of workload. At the end, what we are going to have, because each thread is going to do its own piece of workload. So the partial sum for each thread is going to be different. So partial sum for thread 0, partial sum for thread 1, partial sum for thread 2. I mean, all these partial sums are different. That's the reason why this partial sum should be private. That means the others, they cannot access the other guy's partial sum. Okay, so now, okay, each one has done their own workload. But it's not done yet because each one you only have a partial sum. The final result, what we want to have is this total sum. So what we need to do, okay, we continue. And then there is another one is that, okay, 128 threads. Please, each one, please put your partial sum into the total sum. Okay, so we are going to accumulate the partial sum and we are going to have this total sum. Okay, this is the way for these guys to do that. If we just do, just come back a few minutes, we still remember in the previous part, we talked about that we have 128 MPI threads. They share the workload. They have their P sum. And what they are going to do to find out the total sum, they need to send the message physically. Let me show you here is that if you have this P sum 0, you have this P sum, sorry, this P sum 1, sorry, this is P sum 1. This is P sum 1. Your P sum 2, etc., etc. When you have to do the sum of all these P sums, what you need to do is that you need to have one process receive the results from the others, receive the P sums from the others, and do the accumulation. This is for MPI processes. And here for OpenMP is different. The system is going to ask each thread, okay, just put your result into the total sum. We are going to have these accumulations at the end. But that's not so simple. If thread 1 and thread 2, they are doing this kind of thing at the same time, there is the case, there is the possibility that thread 1 is going to get this total sum, is going to read this total sum and put it somewhere, and then is going to get its partial sum, is going to do the sum, and then put it back in the total sum. It's not just atom operation, it's a few steps. In these few steps, there is the possibility if we have two guys to do the thing at the same time, there is the possibility we are going to mess up the things. And the end, this accumulation could be something totally wrong. Because this is not an atom operation to guarantee that we are going to have the correct answer. What we need to do is that we need to declare this block of code is in a critical region. That means in the critical region, when one thread is doing the operation belonging to this critical region, that's doing this accumulation of the P sum into the total sum, the other guys cannot get into this critical region. That means the other guys cannot do the same thing. Okay? You cannot do the same thing. You have to wait. So then at the end, what we are going to have is that each thread, I mean, one by one, I don't know what's going to be the order, but one by one, all these threads, they are going to put their partial sum into the total sum. And the total sum is what the user wants to have. Okay, and then after each guy has put their partial sum into the total sum, the parallel region is done, is finished. And then because, okay, thank you very much, the 127 threads, you have done your job. right now is the time for your guys to terminate yourself. What I mean is that, okay, I'm thread 0. All the guys, you need to commit suicide. You need to die. Okay, and then after we have finished this power region, we get out of this power region. All the threads created when we get into this power region will be terminated. And then we are going to have thread 0. We still have thread 0. Thread 0 is going to be here to output. 2 to sum is the final result we want to have. Thread 0 is going to print this 2 to sum onto the screen or put the result into a file, whatever, but it's the output. So this is the way for the OpenMP program to run and to stop. So right now, after we have output, this total sum is the time for thread 0 to terminate, to finish everything, and then the thread 0 will be terminated. This is how an OpenMP program is going to run on a node. Basically, a node means with only one operating system instance. This is the definition of a node. So OpenMP parallel programming cannot go beyond one node. It's within a node. Okay, but there is one thing I need to stress out is that OpenMP is open multiprocessing. OpenMP stands for open multiprocessing. And the key message here is there is implicit communication between the threads. There is the parallel programming. There is the parallel computing. There are multiple threads. We didn't say that these threads, they have sent message from one to the other. Like for MPI programs. For MPI programs, all the other processes, they have to put their PSUM physically into this communication network. And this PSUM will be sent to process 0. The same for the other one. Everything will be sent, physically go through the network and send to this process 0. And process 0 is going to do the accumulation of to have this final result, because there really is communication, and this communication is explicit communication between processes. Is explicit because really the data has to be put onto the communication network for the communication to happen, for the receiver to receive. But here, there is still the communication as long as you are doing parallel computing, as long as the workload has been shared. There is a communication, but for OpenMP, we have implicit communication between threads. Okay, this is the OpenMP program. There is another drawing is easier to understand. Somebody has drawn this one and is going to help us to understand. So let's just spend a few minutes to understand this one. This is the parallel region. Okay, this is the parallel region. Okay, this is the parallel region. And here is the declaration of how the guys, they should, how the data should be shared between the threads when they get into this parallel region. There are shared data, there are private data. Anyway, that's the declaration. And then what happened is that when the program get into this parallel region, at the beginning, what you have is that at the beginning, you have this thread 0. At the beginning, it start to run this code, this piece of code from this main function. This is the starting point. There is only one thread, and suddenly you have got into this parallel region here. And what's going to happen is that the system is going to give you a lot of threads, depending on the environment parameter. So you still have this thread 0. This is called master. Usually this thread is called master. And all the other threads are called slave. The slave threads are going to be created by the operating system for you. So for this parallel region, you get into this parallel region. Parallel region starts here, and suddenly, starting from this parallel region, you start to have lots of threads. Okay, and then all these threads are going to execute the same time simultaneously, pretty much on different hardware cores. Okay, and then at a point, you are going to reach the end of the parallel region. Here, this is the ending point of the parallel region. Okay, this is the ending point of the parallel region. Parallel region ends here. When the parallel region is going to be ended, I mean, this is the end parallel region. All these black ones, all these black slaves, they are going to be terminated. Okay, and then afterwards, but there is one you still have, which is the master thread. The master is thread 0. So the master is going to be there. You are going to, after the parallel region, you are going to have your master thread only to continue to output the results to terminate the execution of the main function. I mean, right here, the main function right now is going to be terminated. And this is how the OpenMP works on a server node. Okay, so here it has been shown again, but here this is from the point of view of the system. From the operating system point of view, is that you have this 0 region, and you have this 0 region, you have this ID 0 thread, and then you get into this parallel region, the system is going to fork a lot of threads for you. I mean, the color here is different from the other side. Here, ID 0 is blue. The other slave threads are red. So the system is going to fork a lot of threads to help the thread 0, the master 1. The quantity depends on the system setting. Okay, and then you are in this parallel region. This is the parallel region. You are in this parallel region. And then when you reach the end of the parallel region, all these slave threads will join these master threads. I mean, all these threads will be killed. Well, let's put it this way. And then you are back in the 0 region, and then up to the end of the main program, main function, sorry. This is how it works. So I insist to have this drawing for your guys, is that we are going to reuse this drawing when we are going to talk about this GPU computing. That's going to be very useful, and is going to help us to understand this GPU computing stuff. Okay, This is OpenMP parallel programming, OpenMP parallel program, how it works. Okay, we stop here. We are going to have a rest and we come back later on to continue.